Have scientists found a way to beat the speed of light? Tonight, we're going to talk about one of the most dangerous ideas in modern physics. Not dangerous because it's violent. Dangerous because it may be real. For more than a century, humanity believed the stars were forever out of reach. Einstein's equations appeared to seal the universe shut, locking civilization inside a cosmic prison where nothing could travel faster than light. And the distances between stars are so extreme that even our fastest spacecraft look motionless against the scale of the galaxy. Voyager 1, the most distant human-made object ever launched, has been racing through space for nearly 50 years. In all that time, it has traveled less than 1% of 1 light-year. The nearest star beyond our Sun is more than 4 light-years away. At Voyager's speed, the journey would take around 70,000 years. That means if ancient humans had launched Voyager during the Ice Age, it still wouldn't be there yet. For decades, physicists assumed there was no escape from this problem. The universe had a speed limit. And nature does not negotiate, but then something unexpected happened. A small group of researchers began digging deeper into Einstein's equations, searching not for faster engines, but for loopholes hidden inside spacetime itself. And in 2024, they published a paper that shocked the physics community. Not because they broke relativity, but because they found a way around one of its biggest limitations. A real mathematical warp drive. Not science fiction. Not movie fantasy. An actual solution inside known physics. By the end of tonight, you'll understand exactly how warp drives work, why physicists once believed they were impossible, and why that assumption may have just collapsed. Because the truth is even stranger than fiction. The universe may not forbid warp travel after all. Before we begin, if you enjoy deep space documentaries and explorations into the mysteries of physics, make sure to subscribe. And now, let's step into the mathematics that may one day carry humanity to the stars. The scale of the problem. The nearest star system to Earth is Proxima Centauri, a tiny red dwarf star orbiting within the Alpha Centauri system. Distance from Earth: 25 trillion miles. That number is so enormous that the human brain cannot intuitively process it. So instead, let's shrink the problem into something understandable. Light travels at 186,000 miles per second. At that speed, you could circle Earth more than 7 times in 1 second. A beam of light leaving the moon reaches Earth in about 1.3 seconds. Light from the sun takes just over 8 minutes to arrive. But light from Proxima Centauri takes more than 4 years. That means when you look at Proxima tonight, you are not seeing the star as it exists now. You're seeing ancient light, a message that began its journey across interstellar darkness before many current events on Earth had even happened. And light is the fastest thing the universe allows. Nothing moves faster. Not particles. Not signals. Not information. According to Einstein, the speed of light is built directly into the architecture of reality, which creates a terrifying problem for interstellar civilization. Even if humanity built a ship capable of reaching 10% of light speed, far beyond anything we can currently engineer, reaching nearby stars would still take decades. At 1% of light speed, the trip takes centuries. At Voyager speeds, it takes tens of thousands of years. the galaxy suddenly stops looking like an ocean waiting to be crossed, and starts looking like isolated islands trapped forever beyond reach. Why rockets eventually fail. Every rocket ever built operates on the same principle. Throw mass backward. Move forward. Chemical fuel explodes. Exhaust shoots outward. The spacecraft accelerates. Simple. But there's a hidden trap buried inside that process. Fuel has mass. And the more fuel you carry, the heavier the spacecraft becomes. Which means you need even more fuel to push the extra fuel, which adds more weight, which requires even more fuel. This creates a brutal exponential problem known as the rocket equation. And the rocket equation is merciless. The Saturn V moon rocket remains one of the most powerful machines ever constructed. At launch, it weighed about 6.5 million pounds. Nearly all of that mass was fuel. Yet after burning through enormous quantities of propellant, the rocket only carried 3 astronauts 250,000 miles to the moon. Now compare that to interstellar distances. Proxima Centauri is roughly 100 million times farther away than the moon. You cannot simply build a bigger Saturn V. The math explodes long before you ever reach relativistic speed. At some point, the fuel required outweighs planets, then stars, then entire solar systems. And eventually the equations stop describing engineering and start describing absurdity. This is why serious physicists abandon the idea that chemical rockets would ever take humanity to the stars. Not because we lack ambition, but because physics itself refuses to cooperate. The dream of faster-than-light travel. Throughout the 20th century, scientists proposed increasingly extreme solutions. Nuclear pulse engines, fusion drives, antimatter propulsion, laser sails. Each concept pushed closer toward relativistic speed. But every design eventually slammed into the same wall: the speed of light. Einstein's special relativity states that as an object approaches light speed, the energy required to continue accelerating rises dramatically. Closer. Higher. Closer still. Higher again. Until finally the required energy becomes infinite. And infinite energy does not exist. Which means no object with mass can ever reach light speed. For decades, this seemed final. Humanity could dream about the stars, but never truly reach them. Then, in 1994, a young physicist named Miguel Alcubierre asked a question that changed everything. What if the ship never moved through space at all? What if space itself moved instead? The Alcubierre breakthrough. This is the moment where warp drive stopped being fiction and entered physics. Alcubierre realized something subtle hidden inside Einstein's equations. Relativity limits how fast objects can move through spacetime. But it does not limit how fast spacetime itself can expand, contract, or distort. And we already know spacetime can expand faster than light. The universe itself has been doing exactly that since the Big Bang. Distant galaxies are receding from us faster than light, not because they are flying through space at impossible speeds, but because the space between galaxies is stretching. The galaxies are being carried apart by expanding spacetime. Alcubierre asked, "Could the same effect move a spacecraft?" His answer was astonishing. Yes. At least mathematically. The idea works like this. Space compresses in front of the ship. Space expands behind the ship. The spacecraft itself remains motionless inside a bubble of flat spacetime. The ship never locally breaks the speed of light. Instead, the bubble carrying the ship moves through the universe, like a surfer riding a moving wave. Einstein's equations allowed it. The math checked out. And suddenly warp drive was no longer fantasy. It was theoretical physics. But there was one catastrophic problem. The equations required exotic matter. Matter with negative energy density. Something never observed in usable quantities anywhere in nature. And the amount required was horrifying. Early estimates suggested you'd need more exotic energy than exists in the observable universe, which effectively killed the idea. For a while. Because over the next 3 decades, physicists kept improving the design, and every new refinement brought the impossible slightly closer to reality. The 2024 discovery. Then came the breakthrough. In 2024, researchers at Applied Physics published a paper titled Constant Velocity Physical Warp Drive Solution. And unlike previous warp drive models, this one did not require exotic matter. No negative energy. No violations of known physics. No impossible substances. Instead, the design used only positive energy. Ordinary matter. The same kind of matter found in stars, planets, gas clouds, and human beings. For the first time in history, physicists had constructed a warp spacetime solution fully compatible with known physical laws. That sentence is hard to overstate. It means warp drive may no longer belong exclusively to science fiction. Now, there is an important limitation. This new warp drive is subliminal. Below the speed of light. It does not allow Star Trek-style galaxy hopping. But that misses the significance of the discovery. The real breakthrough is proving that warp spacetime itself may be physically achievable. And once something becomes physically possible, engineering begins. That process can take decades. Sometimes centuries. But history shows it happens. Human flight once sounded impossible. Space travel sounded impossible. Landing on the moon sounded impossible. Right now, no human being has ever warped spacetime into a navigable bubble. No spacecraft has ridden a gravitational wave across the solar system. No civilization has crossed the stars. But for the first time, physicists are no longer asking whether warp drives violate reality. They're asking how difficult they would be to build. And those are completely different questions. Somewhere inside Einstein's equations, hidden for more than a century, spacetime may contain a pathway to interstellar civilization. A method for crossing distances once believed uncrossable. A technology that could one day transform humanity from a planetary species into a stellar one. Maybe not tomorrow. Maybe not in our lifetime. But the door is no longer fully closed. And that changes everything. We might not have them for centuries. The energy requirements are also staggering. Even though the foo's design doesn't need exotic matter, it still needs energy. Lots of it. Accelerating a massive shell of ordinary matter to 90% of light speed requires energy inputs comparable to significant fractions of global power production. We're talking terawatts sustained over hours or days. That's energy on a scale we've never attempted. The instrumentation to test even small-scale warp effects doesn't exist yet. Before anyone builds a full-scale warp ship, someone needs to demonstrate that the effect works at laboratory scale. That means building interferometers sensitive enough to detect spacetime curvature around benchtop experiments. Current instruments can measure gravitational waves from colliding black holes billions of light-years away. But measuring static local curvature from a small matter distribution is a different problem entirely. It requires precision we haven't achieved. Nobody is building a warp drive this decade or next decade. Probably not this century. But the physics allows it. The math is clean. The materials are ordinary even if we can't shape them properly yet. And there's a research community actively working on the problem. In early 2026, less than 2 years after the flu paper, another study suggested the next refinement might already be on the horizon. A follow-up paper from the applied physics team and collaborators revisited the warp drive metric families with more sophisticated mathematical analysis. The central finding was that spacetime can bend further than earlier models assumed. Previous calculations had made certain assumptions about how the warp bubble geometry must blend into the surrounding universe. Assumptions based on mathematical convenience and computational tractability. When those assumptions were relaxed, the equations revealed a wider range of possible curvature profiles. Some of the newly identified profiles correspond to warp drives that use even less energy than the 2024 Fuchsia's design. A few might allow superluminal operation with significantly reduced exotic matter requirements. Reduced, not eliminated, but reduced enough that the problem might shift from impossible to merely extraordinarily difficult. The paper didn't claim to have solved the faster-than-light problem. What it claimed was that the solution space is larger than anyone had been exploring. For 30 years, warp drive research had been narrowing, eliminating candidate designs one by one as they failed energy conditions, stability tests, or other physical criteria. The new result argued that some of those eliminations were premature. That researchers had been searching a subset of the actual solution space and that reopening the discarded regions might yield hybrid designs combining the best features of multiple approaches. Research groups at universities in Germany, Australia, Japan, and the United Kingdom immediately began running simulations using Warp Factory and other numerical tools to evaluate the newly identified metric families, checking which ones satisfy energy conditions, which ones are stable against small perturbations, which ones could plausibly be built with materials that might exist, even if we don't have them yet. The work is ongoing. As of this recording, no paper has delivered a superluminal warp drive that passes every test and uses only ordinary matter. The superluminal barrier remains, but what has changed, subtly but significantly, is the attitude of the broader physics community. Throughout the 1990s and 2000s, warp drive research was fringe. Tolerated in the literature because the math was valid, but not taken seriously as a path to real technology. Conferences didn't feature sessions on it. graduate students didn't write dissertations on it without raised eyebrows from their committees. Funding agencies didn't support it. By the mid-2020s, that changed. Papers on warp drive appear regularly in Classical and Quantum Gravity, Physical Review D, and other top-tier journals. Conference sessions on advanced propulsion draw large audiences. NASA maintains an interest even if EagleWorks is no longer as active as it once was. Private organizations like Applied Physics publish openly and collaborate with academic researchers. Graduate students cite warp metrics in their work without professional stigma. The field has moved from mathematical curiosity to legitimate engineering problem. The engineering might still be centuries away, but it's engineering, not fantasy, and that distinction matters. There is, however, one aspect of superluminal warp drive that needs to be addressed. The reason faster-than-light travel remains so difficult has everything to do with what happens at the front edge of the bubble when it crosses the light barrier. When a warp bubble moves faster than light, it creates something called a horizon. A horizon is a boundary in spacetime beyond which information cannot pass in certain directions. The most familiar example is a black hole event horizon. At a black hole's event horizon, spacetime is falling inward faster than light can propagate outward. Anything crossing that boundary cannot escape. Not because it's being pulled by some overwhelming force, but because the geometry of spacetime itself has changed such that all future directed paths point inward. There's no direction you can move that leads back out. A superluminal warp bubble generates a similar structure at its leading edge. The front wall of the bubble is moving outward faster than light, which means any signal sent from inside the bubble toward the front edge can never catch up. The front edge is receding faster than the signal can propagate. This creates a causal disconnect. The ship's interior is cut off from its own leading edge. A radio signal sent from the pilot's seat toward the front of the bubble would never arrive. The signal would chase the front wall forever, never catching up, never influencing what happens there. From a navigation standpoint, this is catastrophic. During the voyage, the ship cannot steer. It cannot adjust course. It cannot transmit any information ahead of its position. The bubble must be aimed correctly before launch because once it's moving at superluminal speed, the crew has no causal access to the region of space they're heading toward. Any error in the initial trajectory cannot be corrected mid-flight. Any obstacle in the path cannot be avoided. The ship simply plows forward on whatever vector it was set to, unable to respond to changing conditions. It gets worse. A superluminal warp bubble also cannot be stopped from inside. To decelerate, the bubble would need to change its own geometry, shift the distribution of matter or energy in the warping region. But doing that requires sending signals from the ship's interior to the bubble boundary. And if the bubble is moving faster than light, those signals cannot reach the leading edge. You're locked in. The only way to stop is to have external infrastructure at the destination. Pre-positioned equipment set up by an earlier mission that can collapse the bubble from outside. Or some kind of autonomous mechanism embedded in the bubble wall itself programmed to shut down after a certain duration. Neither option is reassuring. The pilot sitting in the control seat has effectively become a passenger, watching the universe blur past through windows that no longer obey normal causality. Some theorists have proposed workarounds. One idea involves oscillating the bubble, switching it on and off at high frequencies so the ship has brief moments of causal contact with the outside universe between warp pulses. The math for this exists in certain models, but it introduces severe stability problems. A bubble that keeps collapsing and reforming might emit catastrophic bursts of radiation with each cycle. The energy released could be enough to vaporize the ship. Another idea is to simply accept the limitation and design missions around it. Warp drives become long-range ballistic devices. You aim them carefully, launch them, and hope they arrive where you pointed them. For pre-planned routes between established destinations, this might be workable. For exploration, it's essentially useless. The horizon problem doesn't prove warp drive is impossible. It proves that superluminal warp drive, if it works, would be a fundamentally different kind of vehicle than anyone imagined. Not a steerable starship you pilot like an airplane. A ballistic projectile you aim and fire with no ability to change course once launched. And there's a second consequence of the horizon that's even more dangerous. A consequence involving radiation. In 1974, Stephen Hawking published a result that shocked the physics community. He proved that black holes emit radiation. Before Hawking's work, everyone assumed black holes were perfectly black. No light escapes. No heat radiates away. They're cold, dark, silent objects that only absorb and never emit. Hawking showed that quantum mechanics changes the picture. Near the event horizon of a black hole, virtual particle pairs constantly pop into existence from the vacuum. Normally, these pairs annihilate almost immediately and disappear. But near a horizon, something different happens. One particle of the pair can fall into the black hole while the other escapes. The escaping particle becomes real, carrying energy away. From the outside, it looks like the black hole is radiating. This is called Hawking radiation. One of the strangest consequences of warp drive physics has nothing to do with propulsion at all. It has to do with time. The moment physicists realized that warp bubbles could, in principle, move faster than light, another implication appeared almost immediately. If faster-than-light travel exists, then under certain conditions, time travel may also become possible. This is not science fiction speculation layered on top of the equations. It falls directly out of Einstein's relativity. One of the strangest consequences of warp drive physics has nothing to do with propulsion at all. It has to do with time. The moment physicists realized that warp bubbles could, in principle, move faster than light, another implication appeared almost immediately. If faster-than-light travel exists, then under certain conditions, time travel may also become possible. This is not science fiction speculation layered on top of the equations. It falls directly out of Einstein's relativity. Special relativity tells us that simultaneity is relative. Two observers moving at different velocities do not agree on what events happen at the same time. For everyday speeds, this effect is tiny. But as velocities approach the speed of light, the disagreement becomes dramatic. Now imagine a spacecraft capable of superluminal travel. From the perspective of some observers, the ship would appear to arrive at its destination before it left. Not because the ship literally reversed its engines through time, but because spacetime itself allows different observers to slice events into past, present, and future differently. Combine two faster-than-light trips in different reference frames, and you can construct what physicists call a closed time-like curve. A path through spacetime that loops back onto itself. In plain language, a ship could potentially return to its own past. This was one of the earliest objections raised against the Alcubierre drive after the 1994 paper appeared. The equations seemed to imply that any practical faster-than-light system would also function as a time machine. And time machines create paradoxes. The classic example is the grandfather paradox. You travel into the past and prevent your grandparents from meeting. If they never meet, your parents are never born. If your parents are never born, you are never born. But if you are never born, then who traveled back in time to prevent the meeting? Physics does not like contradictions. The laws of nature appear deeply structured around causality. Causes precede effects. Information flows forward through time. Every experiment humanity has ever conducted has reinforced that structure. So when general relativity permits solutions that seem to violate causality, physicists become nervous. Stephen Hawking addressed this directly in 1992 with what he jokingly called the chronology protection conjecture. Hawking suggested that the laws of physics themselves may contain hidden mechanisms that prevent time travel from ever becoming physically realizable. His reasoning involved quantum effects near closed time-like curves. As a time machine begins to form, quantum fluctuations in the surrounding spacetime may grow without bound. Radiation intensifies. Energy densities diverge. The geometry destabilizes and collapses before a usable time loop can form. In essence, the universe may protect causality by destroying any structure that threatens it. No complete proof exists. Chronology protection remains a conjecture, not a theorem. But many physicists suspect something like it must be true. Otherwise, the universe becomes logically inconsistent. Warp drive researchers therefore face an unusual challenge. They are not merely trying to build a propulsion system. They are trying to build one that does not accidentally become a time machine. Some proposed warp metrics avoid this issue by remaining strictly subliminal. As long as the bubble never exceeds light speed relative to surrounding observers, causality violations do not appear. This is another reason modern positive energy warp research focuses heavily on subliminal geometries. A subliminal warp drive could still revolutionize space travel. Imagine a spacecraft capable of reaching 90% of light speed without subjecting its crew to enormous acceleration forces. A journey to Alpha Centauri would still take years, but not tens of thousands of years. Relativistic time dilation would further reduce the perceived duration on board the ship. A crew might leave Earth, spend a decade traveling, and arrive while more than a decade has passed outside. Interstellar civilization becomes possible without violating causality or requiring exotic negative energy on impossible scales. And this may ultimately be the realistic future of warp physics. Not magical faster-than-light jumps across galaxies, but practical manipulation of space-time geometry to make relativistic travel survivable. Because conventional rockets run into brutal limitations long before reaching light speed. Chemical rockets are extraordinarily inefficient. The Saturn V that carried Apollo astronauts to the moon launched with more than 2,900 tons of mass. Almost all of it was fuel. Only a tiny fraction reached space as useful payload. For interstellar travel, the problem becomes exponentially worse. The rocket equation, derived by Konstantin Tsiolkovsky in 1903, governs how rockets work. Every increase in desired velocity requires exponentially more propellant. Want to double your speed? You need far more than double the fuel. To approach relativistic velocities using conventional propulsion, the required fuel masses become absurd. A ship carrying enough chemical fuel to reach nearby stars would need to be larger than planets. Even nuclear propulsion struggles. In the 1950s and 1960s, Project Orion proposed a spacecraft propelled by nuclear explosions detonated behind a massive pusher plate. Each explosion would shove the craft forward. In theory, Orion could achieve velocities far beyond chemical rockets. The concept was physically plausible. Engineers at General Atomics built detailed designs. Some versions could have launched payloads weighing thousands of tons. Interplanetary travel times would shrink dramatically. A trip to Mars might take weeks instead of months. But even Orion falls far short of interstellar capability. The fastest projected Orion variants might achieve a few percent of light speed. Impressive by human standards. Still painfully slow compared to the distances between stars. At 1% of light speed, reaching Proxima Centauri still takes over 400 years. Fusion propulsion improves the numbers further. Concepts like Project Daedalus in the 1970s envision fusion-powered starships using pellets of deuterium and helium-3 ignited by electron beams. Daedalus was one of the first serious engineering studies for an interstellar probe. The spacecraft would have weighed around 54,000 tons at launch. Most of that mass was fuel. After years of acceleration, it might reach about 12% of light speed. Fast enough to reach Barnard's star in roughly 50 years. That is remarkable engineering. But it remains generation ship territory. Human crews would either live and die on board or require suspended animation technologies we do not possess. Antimatter propulsion offers even higher efficiencies. Matter-antimatter annihilation converts nearly 100% of mass into energy. No known reaction is more efficient. A kilogram of antimatter annihilating with a kilogram of matter releases energy comparable to tens of millions of tons of TNT. In principle, antimatter engines could propel spacecraft to significant fractions of light speed. In practice, antimatter is extraordinarily difficult to produce and store. Humanity has created only microscopic amounts. The total antimatter ever produced by all particle accelerators combined would barely power a flashlight for a few minutes. And antimatter touching ordinary matter annihilates instantly. A containment failure aboard an antimatter spacecraft would resemble a nuclear explosion. Warp drive sidesteps these propulsion limitations entirely. The ship itself does not accelerate through local space in the conventional sense. Space moves around the ship. The crew inside could experience near-zero proper acceleration even while the bubble travels at relativistic speeds relative to distant observers. This changes the engineering problem from how do we carry enough fuel to how do we shape spacetime itself. Still impossibly difficult, but fundamentally different. And humanity has a long history of transforming impossible-seeming physics into engineering reality. When James Clerk Maxwell unified electricity and magnetism in the 1860s, the equations predicted electromagnetic waves traveling through space at the speed of light. Radio did not yet exist. Television did not exist. Radar did not exist. Wireless communication sounded absurd. Within decades, engineers were transmitting signals across oceans. When Einstein published general relativity in 1915, gravitational waves were a mathematical curiosity. Einstein himself doubted they would ever be detected because their effects were so tiny. A century later, LIGO measured distortions in spacetime smaller than the width of a proton caused by black holes colliding over 1 billion light-years away. The history of physics repeatedly demonstrates something important. Equations often arrive long before the engineering needed to exploit them. Sometimes centuries before. That does not guarantee warp drives will eventually exist. Many theoretical possibilities never become practical technologies. Controlled fusion itself remains frustratingly elusive despite decades of research. But warp physics has crossed a threshold few speculative concepts ever reach. It is no longer pure fantasy disconnected from mathematics. It lives inside the framework of established relativity. Researchers can simulate it, analyze it, test its stability numerically, publish peer-reviewed refinements. That alone makes it extraordinary. And even partial success would transform civilization. A practical subliminal warp drive capable of cruising at 50% or 90% of light speed would redraw humanity's future. The nearest stars become reachable within human lifetimes. Robotic exploration expands across nearby systems. Colony missions become conceivable. The Milky Way is enormous, but it is not infinite. At conventional spacecraft speeds, the galaxy is effectively inaccessible. Voyager 1, the fastest human-made object ever launched relative to the Sun, would need over 70,000 years to reach Proxima Centauri if aimed correctly. A civilization limited to those speeds remains trapped in its home system. But a civilization capable of sustained relativistic travel spreads differently. Even without faster-than-light motion, a species expanding at 10% of light speed could colonize the galaxy in tens of millions of years. That sounds immense to humans. Cosmically, it is brief. The Milky Way itself is over 13 billion years old. This realization leads directly into one of the most unsettling questions in science: the Fermi paradox. If interstellar travel is physically possible, even at subliminal speeds, and if the galaxy has existed for billions of years, then where is everybody? Why don't we see evidence of civilizations that mastered these technologies millions of years ago? Physicist Enrico Fermi famously asked this question during lunch in 1950. Where is everybody? The paradox has only grown stronger since then. We now know planets are common. Most stars likely host planetary systems. Many planets exist within habitable zones where liquid water could persist. The raw ingredients for life appear abundant across the galaxy. And yet the sky is silent. No confirmed alien signals. No visible megastructures. No probes entering the solar system. no unmistakable evidence of advanced civilizations. One possible explanation is that interstellar travel remains prohibitively difficult even for advanced species. Maybe warp drive ultimately fails. Maybe relativistic travel proves too expensive. Maybe civilizations rarely survive long enough to spread far from home. Another possibility is more unsettling. Perhaps advanced civilizations are out there, but they deliberately remain quiet. Or perhaps they travel in ways we do not yet recognize. A warp bubble crossing interstellar space would not necessarily emit obvious electromagnetic signals. A civilization using gravitational engineering rather than radio communication might be nearly invisible to primitive observers like us. The first detectable evidence of alien technology might not be a radio message. It might be an anomalous gravitational waveform, a strange distortion in spacetime, a signature that looks impossible until someone realizes it resembles a collapsing warp metric. And if that day ever comes, humanity's understanding of its place in the universe would change instantly. Because the moment we detect evidence that another civilization has learned to manipulate spacetime itself, we will know two things simultaneously. First, that intelligent life survived long enough to reach astonishing technological maturity. Second, that the laws of physics truly permit pathways beyond the isolation of the stars. There's another reason warp drive research matters even if humanity never builds a working starship. The mathematics behind these ideas may help answer some of the deepest mysteries in cosmology itself. Because once physicists started exploring exotic spacetime geometries, they noticed something surprising. The equations describing warp bubbles overlap with equations used to describe the evolution of the universe. In modern cosmology, the universe itself is already doing something that looks eerily similar to a warp effect. Space is expanding, not galaxies flying outward through static emptiness, but space-time itself stretching between galaxies. This distinction matters enormously. When astronomers say distant galaxies are receding faster than light, they are not violating Einstein's relativity. Locally, nothing outruns light. The galaxies are mostly sitting still relative to their local spacetime. What changes is the metric between them. The fabric of the universe stretches. And because the fabric itself expands, sufficiently distant galaxies can separate from us faster than light without breaking relativity. In other words, the universe already contains superluminal expansion. Inflation theory pushes this idea even further. According to the leading models of the early universe, a tiny fraction of a second after the Big Bang, spacetime underwent an explosive inflationary phase. The observable universe expanded enormously in an unimaginably brief interval. Regions once smaller than atoms ballooned to astronomical scales. During inflation, spacetime itself expanded far faster than light. Again, no local violation of relativity occurred because objects were not moving through space faster than light. Space itself was growing. This realization changed how some physicists thought about warp drives. Instead of asking, "Can we break relativity?" the question became, "Can we engineer locally what the universe already does globally?" A warp bubble is, in some sense, a miniature cosmological event. Contract spacetime in front of the ship. Expand it behind. The vessel rides the changing geometry the way galaxies ride cosmic expansion. And this connection means warp research feeds directly into cosmology. The numerical tools developed for warp metrics also help researchers simulate inflationary models. Stability analyses used for exotic spacetimes overlap with techniques used to study the evolution of the early universe. Even the energy conditions violated by certain warp solutions appear in discussions of dark energy and vacuum energy. Dark energy remains one of the greatest unsolved problems in physics. In 1998, two independent teams studying distant supernovae discovered something astonishing. The expansion of the universe is accelerating. Galaxies are not merely drifting apart from the momentum of the Big Bang. The expansion itself is speeding up. Something is pushing the cosmos outward. That unknown effect was named dark energy, and today it appears to make up roughly 68% of the total energy content of the universe. Ordinary matter, stars, planets, gas, dust, everything humans can directly observe, accounts for less than 5%. Most of reality is something we still do not understand. One interpretation of dark energy involves vacuum energy, the energy inherent to empty space itself. The same quantum vacuum that appears in Casimir effect calculations. The same vacuum fluctuations discussed in warp drive theory. The numbers, however, are deeply confusing. Quantum field theory predicts a vacuum energy density enormously larger than what astronomers observe cosmologically. Depending on how the calculation is done, the discrepancy reaches 120 orders of magnitude. It is sometimes called the worst prediction in all of physics. And until physicists understand vacuum energy properly, nobody can confidently say what spacetime engineering may ultimately permit. There may be effects hidden inside quantum gravity that radically alter our understanding of negative energy, vacuum structure, or metric manipulation. Or there may be hard limits we have not yet uncovered. At the moment, humanity stands in an uncomfortable position. We possess equations that hint at extraordinary possibilities, but we lack the deeper framework needed to know whether those possibilities survive contact with a full theory of nature. Because general relativity and quantum mechanics still do not fit together cleanly. General relativity describes gravity as geometry. Massive objects curve spacetime, and that curvature tells matter how to move. The equations work beautifully on large scales. Planets, stars, galaxies, black holes. Quantum mechanics governs the microscopic world. Particles behave probabilistically. Fields fluctuate. Empty space seethes with virtual activity. The equations work astonishingly well at atomic scales. But when physicists try to combine the two under extreme conditions, the mathematics breaks down. Inside black holes. At the Big Bang. Potentially inside warp bubbles. A complete theory of quantum gravity would unify both frameworks into something deeper. Several candidate theories exist. String theory proposes that fundamental particles are actually tiny vibrating strings existing in higher dimensional space. Loop quantum gravity suggests spacetime itself may be quantized, built from discrete chunks rather than smooth continuity. Other approaches explore emergent spacetime, holography, causal sets, or quantum information geometry. None has been experimentally confirmed, and until one is, warp drive physics remains suspended between known science and incomplete understanding. Some theorists suspect quantum gravity may ultimately prohibit macroscopic warp structures entirely. Tiny fluctuations at Planck scales could destabilize the geometry faster than any engineering system could compensate. Others argue the opposite. They suggest spacetime at quantum scales may be far more flexible than classical relativity implies. If spacetime emerges from deeper informational structures, then manipulating geometry may eventually resemble programming rather than brute force energy engineering. That sounds wildly speculative today. But so did splitting the atom in 1900. The deeper physicists probe reality, the stranger it becomes. Black holes themselves were once considered mathematical absurdities. Einstein disliked them. Many early physicists assumed nature would somehow prevent their formation. Now astronomers routinely observe them across the universe. Humanity has even photographed one indirectly through the Event Horizon Telescope. Quantum entanglement sounded equally bizarre. Einstein called it spooky action at a distance. Yet entanglement is now experimentally verified beyond doubt and forms the basis for emerging quantum technologies. The lesson history keeps teaching is dangerous but important. Nature is under no obligation to conform to human intuition, and warp drive sits precisely at that boundary where intuition begins to fail. Because ordinary human experience evolved in a narrow environment. Low speeds, weak gravity, three-dimensional motion through mostly flat spacetime. Our brains were never designed to visualize curved geometry or relativistic causality. Yet the universe operates according to those rules whether they feel natural or not. A sufficiently advanced civilization might eventually regard spacetime engineering the way modern humans regard aviation. Difficult, technical, energy-intensive, but fundamentally manageable. And if that happens, the implications extend far beyond transportation. Control over spacetime geometry would transform energy generation, communication, astronomy, and planetary defense. Gravitational lensing could become an engineered technology instead of merely an astronomical phenomenon. Humanity already uses gravity naturally when observing distant galaxies. Massive clusters bend light, acting like cosmic magnifying glasses. An advanced civilization capable of shaping spacetime deliberately could construct artificial gravitational lenses, enormous telescopes built not from mirrors, but from geometry itself. Communication systems might exploit metric engineering to reduce effective distances between points in space. Entire solar systems could become connected through networks of stabilized spacetime corridors. Even energy extraction changes under such technologies. Rotating black holes contain enormous amounts of extractable rotational energy through processes like the Penrose mechanism. Civilizations capable of manipulating spacetime safely might eventually harness black holes as power sources. A single stellar mass black hole contains more usable energy than entire stars output over billions of years. At that stage, civilization stops looking planetary. It becomes astrophysical. And strangely, modern humanity has already taken the first tiny steps toward detecting such possibilities. Astronomers now search for technosignatures rather than merely radio signals. The concept is broader. Instead of asking whether aliens are broadcasting messages, researchers ask whether advanced engineering leaves observable fingerprints on the universe. A Dyson sphere, for example, would irradiate enormous amounts of infrared waste heat. A civilization moving stars or constructing megastructures could alter galactic light patterns. Artificial illumination on exoplanets might become detectable by future telescopes. Warp technology would produce its own signatures. Exotic gravitational wave bursts. Unusual lensing effects. Anomalous energy distributions. Strange transient distortions in spacetime geometry. Future astronomy may eventually become capable of distinguishing natural astrophysical phenomena from engineered spacetime events. And if that happens, the universe could suddenly appear much less empty. There is also a philosophical consequence to all of this. One that rarely appears in technical papers but quietly motivates many researchers. Warp drive research forces humanity to confront timescales far beyond ordinary civilization planning. Modern societies think in years. Governments think in election cycles. Companies think in quarters. Even major infrastructure projects rarely extend beyond decades. Interstellar engineering demands thinking across centuries. The first builders of cathedrals in medieval Europe often began projects they knew would not finish within their lifetimes. Some cathedrals took hundreds of years to complete. Generations inherited the work of previous generations. Warp physics may require that same mindset on a far larger scale. The scientists developing theoretical frameworks today understand they will never pilot such vehicles themselves. Many suspect nobody alive now will. Yet they continue refining equations, running simulations, improving instrumentation, and publishing incremental progress anyway, because civilization advances through cumulative effort. The people who first studied electromagnetism never saw smartphones. The mathematicians who explored non-Euclidean geometry in the 19th century had no idea their abstractions would later become essential for GPS satellites and relativistic navigation systems. Knowledge often becomes useful long after its creators are gone. And warp research, even if it never produces starships, expands humanity's understanding of spacetime itself. That alone has value. Every refinement teaches physicists more about general relativity, quantum fields, gravitational stability, and vacuum structure. The attempt to solve one impossible problem spills discoveries into dozens of neighboring fields. This is one reason advanced theoretical research matters even when applications seem distant. The path to practical outcomes is rarely predictable. Laser physics once appeared to be an elegant but useless curiosity. Early researchers joke that lasers were a solution looking for a problem. Today, lasers underpin global telecommunications, medicine, manufacturing, navigation, and data storage. Quantum mechanics once sounded purely philosophical. Now semiconductor electronics power civilization. Warp drive may ultimately fail. But the attempt to understand whether it fails could reshape physics along the way. And perhaps that is the real significance of the field today. Not that humanity is about to leap between stars. We are not. But for the first time in history, the question has moved out of mythology and into mathematics. The stars are no longer unreachable because the gods forbade it, or because nature says no. They are unreachable because the engineering challenge is staggeringly difficult. That is a completely different kind of barrier. Difficult barriers fall eventually, sometimes slowly, sometimes unpredictably. But history shows they fall one breakthrough at a time. The people who first studied electromagnetism never saw smartphones. The mathematicians who explored non-Euclidean geometry in the 19th century had no idea their abstractions would later become essential for GPS satellites and relativistic navigation systems. Knowledge often becomes useful long after its creators are gone. And warp research, even if it never produces starships, expands humanity's understanding of spacetime itself. That alone has value. Every refinement teaches physicists more about general relativity, quantum fields, gravitational stability, and vacuum structure. The attempt to solve one impossible problem spills discoveries into dozens of neighboring fields. This is one reason advanced theoretical research matters even when applications seem distant. The path to practical outcomes is rarely predictable. Laser physics once appeared to be an elegant but useless curiosity. Early researchers joke that lasers were a solution looking for a problem. Today, lasers underpin global telecommunications, medicine, manufacturing, navigation, and data storage. Quantum mechanics once sounded purely philosophical. Now semiconductor electronics power civilization. Warp drive may ultimately fail, but the attempt to understand whether it fails could reshape physics along the way. And perhaps that is the real significance of the field today. Not that humanity is about to leap between stars. We are not. But for the first time in history, the question has moved out of mythology and into mathematics. The stars are no longer unreachable because the gods forbade it, or because nature says no. They are unreachable because the engineering challenge is staggeringly difficult. That is a completely different kind of barrier. Difficult barriers fall eventually. Sometimes slowly, sometimes unpredictably. But history shows they fall one breakthrough at a time. A civilization that learned to fly, split atoms, map the genome, land on the moon, and detect black holes across billions of light years has already demonstrated something important about itself. Humanity is a species that keeps pushing against limits. And somewhere ahead, decades, centuries, or millennia from now, future scientists may look back at these early warp papers the same way modern aerospace engineers look back at the notebooks of the Wright brothers. Primitive, incomplete, full of limitations. But the moment the idea stopped being impossible and started becoming engineering,